this. So I want to go over the 8 queens problem a bit. This is one of my favorite things. I think we'll do another quiz, which is an in-class exercise featuring this puzzle, the Towers of Hanoi, on Wednesday. I'm so used to this being a Tuesday, Thursday class. So let's get this out of the way, and then we're just going to try our best to maneuver this so that we can get a view. Let's go ahead and see. We recorded some higher quality videos. They just haven't been rendered yet involving this chessboard. So let's go ahead and see what we can get here. Aux HDMI. Okay. But I think this will work. Yes. All right. So for this example, I'll use pawns. All right. Actually, I'll use, since I'm going to be using 4 as opposed to the whole chessboard, I'll use the kings and the queens for this one. So just pretend the queens are the kings are also queens. All right, and for this also we'll be taking a look at a 4x4 section of the board rather than a let's see. Yeah, we'll be taking a look at a 4x4 section of the board rather than a full 8x8. This algorithm's the same no matter how many rows and columns. You just need an equal number of rows, an equal number of columns, and an equal number of queens, right? So you can have a 4 queens problem in a 4x4 chessboard, and you could have a 64 queens problem, although God help you trying to do that over there. So, and what we're using is the exhaustive, we're using basically an exhaustive search algorithm. We're searching for basically the first solution. So that's a key there. There's multiple unique solutions for the 8 queens problem, but we're just looking for a solution. There's like 92 something, there's 92 or something, and they're like mostly just rotations of each other. But for this one, we're just, again, looking for 1. Now, so the way this algorithm works is that this is different, by the way, than a brute force algorithm. And again, I'm going to go ahead and put my pen over here, right? We're just working on this section of the board, this 4x4 section of the board. So that's all that exists. Forget this half, right? So it's different. So doing an exhaustive search is different than doing a brute force algorithm. A brute force algorithm means we would try all possible combinations of placing 4 queens on this 4x4 board. So we try this one, right, which is obviously wrong, but it's wrong for 2 reasons, for more than one reason, right? We've got multiple queens like here, we've got a conflict here, 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 and here, right? So that would check that thing, but it would also check this one, and this one, and this one, and this one, and this one, right? All those are wrong, right, for more than one reason, right? So a brute force basically wastes a lot of search by basically saying, hey, we've put down this queen and this, if we know this queen and this queen is here, right? We've got these 2 queens down. We shouldn't need to search anymore, right? We don't have to search this combination, anything involving this, or this, or this, or this. We already know that those won't be correct answers, right? So a brute force answer would look at basically, it would be like 16 choose 4 combinations we'd have to check, right? To use combinatorics terminology. And if you haven't taken combinatorics, that's okay, right? But 16 choose 4, right? Because we'd be basically going down a bunch of branches of searching that we don't need to look down, okay? On the other hand, if I were to look at what we do with our algorithm here is that we basically look at one row, we try to solve one column at a time, okay? We try to solve one row at a time. We say, okay, there's 4 queens, 4 columns, 4 rows. So what we're going to do is we're going to say each of these queens gets a column, okay? Each of these gets a column. And what we're going to do is that we're going to start with the first column. We're going to put a queen here, okay? And we're going to ask, is this a safe spot? Does the queen come into conflict with any other queens that have thus far been placed? No. Okay? So then we go and move on to the next column. Okay? So we move on to the next column. Is this a safe spot for the queen? Right? This is the part of the algorithm that says for position on board. right? Can we put the queen here? No. Here? No. What about there? We can put the queen there. Great. Okay, so there we call solve position plus 1, right? The next position, the next row. Okay, for choice in our position. We can either put the queen here, but that won't work. That's not safe. Can't put it here, can't put it here, can't put it here. So we just went through all the positions there for that column, right? So we return false, which means that basically putting the queen here, after putting the queen here, is a dead end. So having this queen over here, can't do that. So we move forward. We say, can't put it, we couldn't put it here, couldn't put it here, couldn't put it here, so we're going to advance the queen 1. So we go on and put down another queen. Can it go here? No. Here? Looks like it. Looks like we can put the queen there. Okay? Now, so we call the next column. Can we put the queen here? No, 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 no. Dead end. All right? So we backtrack. Can we put... So now I advance this queen 1. Can I put it here? No. Can I put it here? No. So we have to backtrack. I'm out of options here, so I have to backtrack again. So now we move this queen down by 1 space. And we call, okay, solve position plus 1. Put a queen here. Can't put it there, can't put it there, can't put it there. Okay, have to put it there. All right, what about over here? This looks safe, actually. So, okay, finally, what about this space? This row. Can't put it here, here. Oh, but this works. Okay, so I call position plus 1. I call solve position plus 1. Now this is out of bounds, which has been for the rest of this class a terrible thing to do, right? To get out of bounds. But in this particular scenario, this doesn't, if there's no more queens to place, we return true, which means that we pass the return back because it says, hey, you're done, you reached the end. So then this the method call for solving this position, this column, says, okay, I'm going to return true to let the person who called me know I reached a solution. And he goes, great, we reached the solution. So I'm going to call the person who called me and tell them, or return a call to the person who called me to say that we just reached the solution. Then this one will pass back and say, hey, we just reached the solution. We just reached the solution, and it goes back to the main call function, right? Now, the way this recursion works is that essentially trying to solve this problem all at once is too huge. So what we've done is we've reduced this problem to a completely local solution. We ask ourselves, can I put a queen in this space in this column, right? For each row in this column, can I put a queen here? If I can, try to solve the next column. Make sense? All right. Okay, so once you get that down, the hardest part is actually checking where I can, checking to see if your space is safe, actually. Because a queen can move in 8 directions, right? I'll actually use a queen here. A queen can move in 8 directions, right? No, up, down, up, down, left, right, and then all the diagonals too. That's 8 checks you have to do, right? Well, it turns out, no. You don't have to do 8 checks. We can be lazy about this. First off, we've already established that you can only have 1 queen per column. So so long as you enforce that rule that you're only going to be putting 1 queen per a column, guess what? You don't have to check the column. Okay, we're down to 6 checks. Furthermore, because we're placing queens from column 0 to column 7 in that order, and we're always backing up and moving forward, we're never going to be like, okay, we're in this position right now. Okay, now we got to find a place to put this queen, right? We're never trying to solve this row in the middle. It's always like, okay, we need to find a place to put this queen right over here. Because of that, there's only ever queens in one direction. They're always to the left, right? So if I'm trying to put a queen down here and see if there's a safe space, I don't have to check in this direction, or this direction, or this direction, right? So the only directions I have to check are diagonal up and to the left, diagonal down and to the left, and to the left. So I only have to go this way, and this way. Make sense to everybody? So that actually makes it easy. Now, how do I check? to make sure that that's okay. What you want to do is basically say, hey, I'm going to start from this place where I want to put a queen and ask, okay, is there a queen in this direction before I hit the out of bounds? Is there a queen in this direction before I hit the out of bounds? And is there a queen in this direction before I hit the out of bounds? My best advice to you is to remind you, you can actually put multiple conditions inside of your for loops, right? You can go like while rho minus I is greater than or equal to 0, and column minus I is greater than or equal to 0, right? For checking the up and left, right? It's because you're only ever using one variable, right? Right? Well, you're only going to be ever using an I, right? Because we're only subtracting one, and you don't need an I and a j because you're going up and to the left. You're going up at the same rate you're going to the left, right? So you only need one variable when doing that check. And if that doesn't make sense now, don't worry, it will once you get there. Okay, so how would I go about programming this in an effective manner to make sure that I don't have just a mess at the end that I'm trying to debug? The first thing I do is program not an 8 queen solution, but a 8 rooks solution. A rook being a piece that can only move that can move up and down and left and right, but can't do the diagonals because the diagonals are a hard check to do, right? So I just program in, okay, basically a test to make sure there's nothing in the same row and nothing in the same row as me. That's a pretty easy check to do, right? Okay. Then program the recursive solution. Translate the algorithm I gave you into a solution. Okay. And your solution should then look something along the lines of this. Is this a safe space? Yes, it is. Is this a safe space? No. Yeah. Yes, because we're not checking diagonals yet. Is this a safe space? No. No. Yes. And then, is this a safe space? No, 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 yes. We're done with the puzzle, right? So you'll get that solution, so long as you're not checking diagonals. Once you get this, you've confirmed that the recursion is working. It is 100% working now. Awesome. Great. Okay? So then once you got that, program in the diagonal portion, and then you're done, right? So it's actually, once you structure it like that, it's not too bad. I would also program in checking the row, checking the up left diagonal, checking in the bottom left diagonal as their own functions, right? That could be called by an isSafe function, right? So you can check is row safe, is up diagonal safe, and is bottom left diagonal safe, right? By calling all three of those functions, you can program one at a time, right? You can program one at a time and then basically confirm each one is working before moving on to the next one. Okay? So any questions on that? On the 8 queens puzzle? If you are trying again, and so for the knight solution, by the way, for the knight's tour, just remember that it's kind of tricky. It's just kind of tricky to do that on a large board. Again, I do it on a 4x4 board for the knight's one. Remember, and the most issue you're going to have is just making sure that you don't accidentally try to move out of bounds or something with the knight's one. Just making sure that those checks are in and figuring out, I think, the 6 ways that your knight can move. All right. Any questions on those so far? All right. Would people like me to talk about the Sudoku one? I don't know if I've covered that in class yet. Have I? In lecture? Nope.
Talk about how you handle checking the box.
Yeah. Let's go ahead and talk about the generalized algorithm, and then I'm going to talk about checking if it's safe. Right? So you'll find that these algorithms are actually kind of the same, right? The checking to see, is it safe to put this thing here, right? The overall, the recursion is the same, but the checking to see, is this a valid place a valid choice to make is the same. So let me go ahead and Control Shift. Okay, and so boom, boom, boom. All right, so let's go ahead, turn this off. All right, so let's go to, I don't think I pulled up the New York Times, right, yet in class, the Sudoku puzzles from the New York Times. So Sudoku became popular, I'm not sure when, maybe a decade, 2 decades ago. Now, this is a famous, basically puzzle that gets put in newspapers, like the crossword. Except you don't have to know random trivia for the crossword. I really should try the crossword more often. And people like it because you have to use logic to solve it, like saying, okay, so I can't put a 1 here. What goes in this square? 1. I mean, a 3 would work, so we're going to put down a 3 here and I knew that because there wasn't a 3 in this thing, or a 3 in here and a 3 in here, right? And then you kind of just use logic to kind of figure the rest of these out. Like, I can't put an 8 here or a 7, so what is left here? I can put a 1 here, right? And so on and so forth. So you basically just use logic to solve this one at a time. Your computer, on the other hand, the algorithm we're using is not that. It was written by, I'm not sure if it was like one of the founders at Google, who basically got really annoyed with Sudoku and his wife doing Sudoku puzzles because he thought it was a very silly puzzle. The algorithm that we use to solve this is very silly. Instead of doing this, we just solve it like a 4th grader would, which is that we try 1 here, then 2. Oh, there's a solution. There's something that works, so I'm going to go on to the next box. Then I'm going to go and run my finger across the keyboard and go, oh, there's an 8. The first thing that worked was an 8, so I'm going to go on to the next one. Oh, nothing worked there, so I've got to erase my choices, and I've got to backtrack. So on this square, when you hit an empty, I'll do that next time, but anyway, 9, so we advance this by 1. Then we go on to the next square. This next square already has a number in it, so we're going to go up and call the next square, right? So that's a base case. If we already have a number in there, in the row, right? Sorry, if we already have a number in this row-column combination, we go and solve row column plus 1. Okay. Next, we go on and we just try and put numbers there. Oh, can't put a 9 there. Okay, so we backtrack. 4, 5, 6, 7, 8. Okay. Put a 9 there. Can put a 3 there, and then we just keep going forward in the same vein, and I've got to get this actually all the way to the end of this line. So we've complete a line. So now what we say here is now, since column is equal to right now 9, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Column is equal to 9. So now what we do is we say, okay, if column is greater than 8, set column equal to 0, so we're back at the initial column, and then we do row plus plus to go on to the next row. Make sense? So we set the column back to 0, and we go back and we go down to the next column. Now, once we get all the way to the end, how do we know if we're done? We ask if row is greater. After we increment, we ask if row is greater than 8. And if it is, guess what? There's no use in checking anything in this row because it doesn't exist. Okay? All right. So now for the, now again, the solution. So here, again, you're just moving over 2 variables to figure out your position, right? Your row and column, but you're only advancing the column at once. And if you want to test this, just like look for, like, Google this term, like, hardest Sudoku puzzle ever, and just, like, hard code that in as your board. Right? Use zeros for blanks, spaces, and, just let your computer go at it, and it will be done in like a second. Now there was a question as to how the heck do you solve this whole checking to see if you have the same thing in the 3x3. Well, the way you're going to do that essentially is that I'm going to put a 4 here. How do I know it's not valid? What I'm going to do, I need to look for something that actually, let me see. Can I put a 9, 8, 7, 6, 5, 2? There. No. It's not giving me it's not giving me one that is like, there we go. Okay. I only wanted to have a wrong thing that was in the same square as it, right? Okay, so how do we know that that's wrong? Well, what we do is that we check everything in its square. So we check, okay, is there a 1 here? We want to put down a 1 here. Is there a 1 here already? No, 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 yes. And so we're done. So we say that's not a safe space. So how do we do that? Well, the first thing the way we do that is that we're going to run through basically this 3x3 grid. Okay? But how do I know which 3x3 grid I'm in? How do I know which one I'm in? Right? I've got to find basically what I got to do is I start from the top left corner of my little 3x3 board, and I run through all of these. But how do I know which one? And the answer is, like all annoying tricks in computer science, is to divide using integer division. So notice that our 9x9 board is actually split up into a 3x3 of 3x3s, right? It's a 3x3 of 3x3s. Okay? So this is 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, right? Now, how do I know which square I'm in? Well, if I divide both my row and my column by 3 using integer division, right? So let's go back to this example. I want to put a 1 over here. Okay? I'm going to put a 1 over here. This is, let's see, well, what row is this? This is row 0, 1, 2, 3, 4, 5. So this is row 5. Okay? I literally do have to count. And then this is column 7 because this is 8, 7. Right? So this is row 5, column 7. Okay? I need to start checking from here. How do I do that? Well, what I'm going to do is I'm going to divide 5 by 3 and 7 by 3. What's 5 divided by 3 in Java? 1. What's 7 divided by 3 in Java? 2. So that gives me row 1, column 2. Well, that's cool, isn't it? Row 1, column 2 in this. Okay, well, how does that help me, Professor Rosen? Come on. And so now we divided by 3. And now if we then multiply what we got by 3, watch what happens. Multiply 1 by 3, we get 3. And multiply 2 by 3, we get 6. And that will get me this. So if you divide by 3 and multiply by 3, that will end up with the upper left corner of each of those 3 by 3 grids. And I think you can figure out the rest from there. Okay, so dividing by 3 is like this super useful. Using integer division is a super useful trick. I don't know how I figured that one out, but I did. But the idea here is that why does that work? Well, what we're trying to do is get the upper left corner of this, right? The upper left corner for any square in here is 0, 0, right? And all these dimensions are 0 through 2 and 0 through 2. If I divide any of those by 3, I'm going to get 0, right? Here it's 0 and 1. So if I divide any of the rows by 3, that's going to get me 0. And if I divide any of the columns by 3, it's going to get me 1 because column 3 divided by 3 is 1, column 4 divided by 3 is 1, column 5 divided by 3 is 1. Right. Does that make sense to everybody? So you divide by 3 and multiply by 3 to get to your top left corner of your 3 by 3 grid. And then you just iterate through. You'll need a nested for loop to do it. Right? Checking, okay, the row and column in this. So hopefully that answers your question, right? All right. So any other questions about Sudoku? Now, for Sudoku, there is an extra credit, right? There is, and that one involves file reading and writing. Have we gone over file reading yet in this class? Do people know how to read files? Yeah? Does somebody not know how to read files? Okay. So let me go ahead and just go over how to read files quickly so that you guys can get that done. But while I'm getting that pulled up, let's go ahead and take a quiz on recursion. And the password to that quiz is 12345, and I have to publish it. So it's called Recursion Quiz, and the password's 12345. Same combination that's on my luggage.